Joel Graff, and today we're talking about engineering in the wild, growing open source solutions for engineering problems. Now, what do I mean by engineering in the wild? Not that much, really. I just kind of needed a catchy title for my talk. But when we talk about open source software, which is a more organic sort of community-driven type of software development versus the more traditional means of software development that we're all familiar with proprietary software that's produced by a private firm and is considered their trade secret or intellectual property, you do end up with a kind of nice analogy comparing one to the other as wild versus domesticated. And I think if it kind of helps to look at it in those terms as we compare them. So to get started, when I'm talking about it today is what value is there then in using this new, and it's really not that new, it's been around for 30 years, but using this newer form of software development of open source software in more traditional engineering domains where the primary software packages that we're used to using are entirely proprietary. Is it a viable way of doing engineering, and what does it take to actually get there? Well, before we can actually explore that, we need to first make sure we understand what the differences are between these pieces of software. So when we talk about proprietary domesticated software, the kind that we're most used to, we're talking about software that is intellectual property of the vendor which produces it. It is a trade secret. Having the source code which produces that software is in fact a crime under US patent law. As a result, those trade secrets are not available. They're not transparent. They are not available for auditing. All right. So when we have security issues or questions about the robustness of the software or the dependability of the software, we can only query the vendor and have them tell us what they think. In other words, we can't really know for ourselves if what they've produced is good quality software. We just have to simply take their line when they say, just trust us. Ultimately, it's important to remember that this type of software serves the vendor's bottom line. Above all else, it serves the vendor's bottom line, which in most cases is a profit margin. Now, fortunately, the vendor's bottom line is very intimately tied with the user's needs because, frankly, if they're not going to meet the user's needs, the users aren't going to pay for their software. However, there are times when, and it happens frequently enough, a certain user base that has come to depend upon a software that's produced by a vendor is left out in the cold. And perhaps that user base has shrunk over the time, or the software becomes too difficult for the vendor to maintain. And as a result, the vendors is at their leisure able to simply discontinue the development of that software. So as a user then, it doesn't matter how much time, how much money, how much data you've put into that application. If the user chooses to no longer support it, you're done, because in the end, you don't actually own that software. The vendor does. They never give you ownership rights. They only give you the use of a license that gives you the right to use that software under their terms and their conditions. Now, this isn't necessarily a bad model for software development, and is really simply the continuation of what we have done for over 100 years now in a more analog domain into the digital domain. After all, Thomas Edison was a very big fan of the patent system, and he used it very effectively to his benefit. And one of the major advantages that we get then with proprietary software is that it becomes highly optimized. And the reason for that is because it's well funded. Whatever um, money that the vendor money that the vendor needs to do the development of the software can be obtained by selling the software for a substantial price. And with that money, they can hire PhDs and smart programmers and the like to help them further develop and tweak the features of that software and make them even better with each release. And we see that happening, especially in the engineering domain. Bentley, for example, in their latest microstation packages, they've created this suite of products that are all well integrated. One of the more impressive ones that I remember seeing, and it's been a few years now, is and I forget the name of it, but the one of the representatives was demonstrating taking a picture of their kid's bicycle and producing a 3D model of it in Bentley MicroStation. From that, using that photogrammetry technique and cloud data, they were able to reproduce a real 3D model of it, and it looked really, really good. Now, that sort of technology is available freely as well, but very few people or very few options exist that could even begin to approach the quality that you get with Bentleys. And that is obviously one of the major advantages to using proprietary software. So by comparison, when we talk about open source software, a more wild or organic form of engineering software development, we're talking about a piece of software whose code base is open and it's auditable, right? So if the developers tell us, yes, this software is secure, no, there are no government backdoors in it, no, there are no, major bugs, anybody who has the ability to understand software language can actually look at that and verify their claims. There's no secrets when it comes to open source. Second, open source software is the property of the community that supports it. Now, it may be, trademarked or copyright, a few key developers in the project, but in the end, without the community, the software is nothing. And it becomes the real property of the community that uses it. And as a result, if you're a member of that community, or even if you're not, you're free to take that software and do with it as you please. You can modify it, you can redistribute it as you like, whatever thrills you, with really little or no restrictions, except that you can't turn it around and sell it for a major profit as though it were your own. One of the major advantages to open source is it provides more options to overcome code fragility. And I think I had that on the last slide and neglected to mention it. Code fragility is this issue where when a piece of software is developed over time, sometimes some of the code that it depends upon becomes, well, as technology advances, it becomes less functional, less reliable, it breaks more easily, or perhaps because the software developer was in a hurry to meet a deadline, they did a bad job writing code, and that code becomes something they depend upon very, very heavily, and they're constantly patching it, trying to keep it alive. This is what we call code fragility. It breaks easily. You can barely do development on it without it breaking. And in proprietary environments, this can be a very difficult problem to overcome. Whereas in open source, dealing with code fragility issues is at least a little bit easier, because not only can a community target a problem and several developers, or maybe even tens or hundreds of developers from all over the world propose solutions and go after it. But if perhaps there's a disagreement in the community, maybe some people think that this part of the code base is fragile and it's a problem and we need to get rid of it, and others say, no, it's not a problem, it works exactly as we intend. Well, those differences can be resolved because those that disagree can do what's called a fork of the project. They can literally copy it and begin their own project, and they can run in parallel, and they can get rid of the code they want, and they can bring in code that that maybe they prefer instead. And those projects can run side by side, and time will tell which is going to be the better solution. But those options give a lot more leeway then in developing open source solutions that are more robust and more secure and more stable. Now, one of the problems that people often cite when it comes to open source is that there's a lower degree of optimization, that the features take longer to develop, or they don't work quite as well as they do in their comparable proprietary solutions. And this is often true. And, and many often cite, well, it's because the developers just don't know what they're doing, which is a bias that actually is not true. Many times the developers on an open source project are professionals in their field. They use the commercial counterparts. They know what the software needs to do. They know what the critical features are. If those features aren't present, it could be for one of a number of reasons, that there is a lack of money, a lack of time, a lack of resources, or perhaps those features just are not considered to be critical for the mission of the project. So one great example of the differences between open source and closed source software, proprietary software, and how that can be a very ugly thing is Zoom, the software we're using today to host this little teleconference. In July of this year, it came out that Zoom was not being perfectly honest about how it was handling encryption during conference calls. Now, encryption, if you don't know, is simply a way of hiding data, so that when it's transmitted over the internet, that some bad actor can't intercept it and do with it as they please. And I'm sure all of us are familiar with this. If you're familiar with the transition where we used to type http://www.google.com or something like that. Nowadays, it's HTTPS, S for secure. And what that means is that whenever that transmission is sent over the internet, whatever your information is that you're sending back and forth, it's encrypted. So someone in the middle can't pick it up and read it. The most secure kind of encryption that's out there is called end-to-end encryption, where the data is encrypted on your computer before it leaves it, and it is not decrypted until it is received on the target computer. Perhaps you're sending someone messages, or you're having a video conference with others. For some time, Zoom has claimed that teleconferencing was end-to-end encrypted, and the federal government found out that that was not in fact true. And this is a real problem because all of this time we've had no way to validate that. We simply had to take Zoom's word for it. Why? Because it's proprietary software. It's closed source software. Their code base is not open to auditing. And that's a major issue when it comes to security. By comparison, there is an open source alternative to Zoom. It's called Jitsi. And Jitsi also provides encryption, but they've been honest about it. They have not been able to until recently provide end-to-end encryption. They provide instead something called peer-to-peer encryption, but they do provide a way for you to enable and effectively enable end-to-end encryption without being able to call it specifically that. And they give you clear instructions as to how to go about it. So in all this time that I've been talking about open source versus proprietary, the concept of free has sort of been implied, but really not clearly understood. When we talk about open source software, if you're familiar at all with it, you know it's generally free. It doesn't cost you anything to use. You can download it for free, you can use it for free. And a lot of people say, well, that's why we should use it because it doesn't cost us a lot. We don't have to spend crazy money for, proprietary licenses and so on. And it makes sense in a hobbyist or a small agency or a small business level. But when you're talking about middle to larger size businesses, consultants which make tens of thousands, hundreds of thousands, millions of dollars a year on contracts and use, say, Autodesk or Bentley software to do that, well, the value of the contracts far exceeds the cost of those licenses. So to argue that open source is free and therefore better on an economic level isn't really a strong or viable argument when you're talking about professional engineering organizations. Again, that's better suited for your hobbyist or for your smaller agencies and that sort of thing. Really, when we talk about free and open source, the context of free that matters the most is free speech. We compare the two as free speech versus free beer. Free beer being the economic side, free speech being the side of personal expression. I can take this software and I can do with it as I please. I actually own this software. It's mine, right? And I can modify it. I can do as I please. Someone cannot come along sometime later and just take away my right or my ability to use it. That concept of free speech is also what guarantees security, right? Because it requires that transparency, it requires that ability. So when you see the term free in open source, don't think free as in beer, think free as in speech. Free as in freedom, or free as in expression. So what examples do we have of engineering in the wild, of open source engineering showing up in professional domains where it may not have so much in the past? Well, the first and easiest example is software engineering. Because really that domain is going to need the value of open source far more than a lot of your other professional domains. What I mean by that is artificial intelligence or machine learning, network stacks, network security. These are domains where the software needs to be robust. It needs to be secure. Any bugs or problems that are found in the software need to be iterated on quickly and fixed right. And it's much more reasonable to expect that from a software project which is auditable, which is transparent, which people who have a vested interest in it, all the world, across the entire world, can engage that and can tackle that problem and collectively come up with a solution. More often than not, when security vulnerabilities are found in open source software and are exploited, very often it is the fault of the person running the system that installed the software because they failed to keep it updated rather than the software itself because they never caught the security issue. That's much different than your proprietary solution where you don't have the ability to go in and deal with that problem. You simply have to talk to the vendor and pretty please, can you fix this for us? And they'll get to it when they can. And whether or not they've actually fixed it, well, you'll just have to trust them. Now, in our more traditional engineering domains, we've been predominantly driven by proprietary software, and understandably so. Why? Because in your more traditional engineering domains, well, we may be technical people, but we're not programmers. We don't have that much interest in software. We don't really want to get into code. Most of us don't have the time or energy or really brain power for that because developing is hard. It's really hard. And so it makes good sense to pay for a developed package that meets our needs as engineers, that does the heavy lifting for us so that we don't have to do it for ourselves. Proprietary software makes a lot of sense, and I certainly wouldn't argue that. Now, are there free software tools in our more traditional engineering domains like, civil engineering or hydraulic or structural? Well, yes, of course there are. and they are government tools. A good example is HECRAS, which is developed by the Army Corps of Engineers. Now that is a free beer tool, right? You can download it for free, but it is not a free speech tool. The source code is not available. And typically when you find free tools in our more traditional context, they are not open source tools. And one of the major biases that you'll encounter in these domains, largely because your traditional engineering uh, practitioner is not so familiar with this proprietary open source dichotomy, is that they'll look at that open source solution and say, well, if it's free, it can't be good. You get what you pay for. And that in itself is also largely incorrect in many cases. Now, and that's not to say that open source is as high quality as proprietary. In many cases, it's not, and it's very obvious that it's not. A lot of people complain that open source software doesn't have a very good user experience, and that's simply true. Because you're dealing with a project that has, limited resources, limited developers, and when it comes to doing development, they're going to want to spend their time on getting the necessary features working right, not worry so much about how pretty the icons are and things like that. So there is always that side issue, but it's important to remember that just because it's free, it doesn't mean it's not any good. So one of the major advancements that we have seen in terms of software technology in recent years in the more traditional engineering domains is the rise of parametric CAD. Now, parametric CAD is a way of producing 3D models, as I'm certain many of us are well aware, but it's a way of producing 3D models that differs substantially from the traditional method of mesh modeling. Mesh modeling is creating a model by building a surface out of points and edges that form faces, usually triangular or square faces. This is the modeling technique that's used most often by animation companies like Pixar when they create Toy Story or something like that. It's really very much analogous to sculpting in 3D. In fact, that's exactly what it is in a lot of ways. It's sculpting in 3D. A great example there is a model on the left from a movie that was produced several years ago called Big Buck Bunny. But I can tell you as an engineer that when I want to create, as a civil engineer in highway design, for example, when I want to create a 3D model of a highway, I don't want to sculpt it because frankly, it's not that fancy. I want to lay out a cross section and tell it to go for miles and let the computer do all the work, right? You can't do that in traditional mesh modeling. You can, however, do that with parametric CAD. And if I don't like how wide a lane is, I can go in and change that lane width from, say, 12 feet to 24 feet or whatever thrills me, and the model recalculates itself. In mesh modeling, I'd have to go and pull all of those vertices out and widen it by hand, one point at a time. So there's major advantages with parametric CAD. Another example is that it gives you a nice history of what it takes to have created that model in the first place. And we're starting to see it make inroads in domains like mechanical, architectural, civil, excuse me just a second, civil, and various other engineering disciplines. We're also seeing it make inroads, and it's nearly ubiquitous now in the hobbyist culture for the purposes of 3D printing. Now, if you take a look at the picture on the right, there's a good example of some parametric CAD modeling that I've done in a software that we're going to talk about in a little bit called FreeCAD. Now, what you're looking at on the screen there is the joystick case for an Apple IIe computer. And I'm certain there's a few of us out here that remember those Apple IIe computers that were popular in schools that maybe some of us played Oregon Trail on. Which incidentally, if you didn't know, Apple's best-selling computer of all time was in fact the Apple IIe. And I'm a retro computing hobbyist. I enjoy buying old computers like that, old 8-bit systems like that, refurbishing them, taking the yellow out of the plastic, resoldering, replacing leaky capacitors, and then, doing something fun with them. And I'm an active part of some of the Apple IIe communities worldwide. And one of the things that's come up frequently is the need for replacement parts for aging plastic that gets very brittle and breaks very easily. And so as I've gone and refurbished these systems, I've taken the time to boot up FreeCAD and model them in 3D and then produce 3D models that I make freely available on Thingiverse. It's a lot of fun. And I end up creating models that are interchangeable with the original pieces by doing that. And it's been surprisingly appreciated in the community. So I really enjoy being able to contribute in that way. Uh, but when we talk about FreeCAD, FreeCAD itself is an open source project that was developed initially in Germany about 15 years ago. It has yet to reach version 1.0. And that's not because there's been a lack of development in the last 15 years, but it's because the developers are very picky. It's a very functional program, but they're of the opinion we're just not there yet. Why? Because these guys are pros. They know Fusion 360. They know Autodesk Inventor. They use professional parametric CAD software every single day. So when they go home at night and hack on the FreeCAD project, they know what their project has to look like if people are going to take it seriously. So right now we're at release 0.19, just about actually. The software itself is written in C++, which if you're going to write a high-performing software, you're going to write it in C++. It has been the standard for probably 30 years now. And it has a Python scripting backend. Now, what that means is if you've ever written a macro in Microsoft Office or an Autodesk or a Bentley product, you've used Visual Basic or Visual Basic for Applications, which is a language that Microsoft put out in 1996, and it reached end of life in 2008. It's been a dead language for 12 years now. In open source, we don't use Visual Basic. Number one, because it's proprietary. Number two, because it's dead. So we use Python instead, and Python is a very powerful scripting language. People do machine learning with Python. And the neat thing about having a Python scripting backend on an open source project is that you can take two completely unrelated open source projects and you can make them talk to each other through Python. We've seen people take Arduino and hook up maybe a switch or a varistor, a knob or a dial to an Arduino, and using some Python script, get it to control, say, a robotic arm in FreeCAD. It's absolutely neat what I've seen some people do, making FreeCAD connect with other software or even hardware using Python. One of the major features of FreeCAD that you don't find in proprietary software is that it is eminently scalable using modules, or what we call workbenches. Our users create workbenches to design 3D objects of all different types. Gliders, propellers are two popular examples. I have been working on developing a workbench for civil highway design, and we'll be looking at that in just a second. But ultimately, the question to ask here is FreeCAD a viable alternative to proprietary software solutions that are out there today? The answer is no, not yet. Probably not for a long time, but it's getting close. This is a graph of FreeCAD's GitHub stars. Now, GitHub is a website, a software repository where open source projects, by and large, are hosted. So if you want to look at the source code for an open source project, like I don't know, Apache or something like that, you can go to GitHub and you can check out their check out their code. Well, FreeCAD, of course, you could go there and you could look at FreeCADs. The stars system on GitHub is kind of like a like on Facebook, right? So as you're scrolling through Facebook, you see a post by your buddy, you click like, right? And it means about the same thing. It doesn't mean that the person who gave GitHub a star actually cares that much. They just thought maybe it was neat or something like that. They may not know anything about it any more than you may have actually paid attention to your buddy's Facebook post. You just saw that it was by your buddy, so you like it. But the fact of the matter is the star system on GitHub does tell us something about the life and the health of an open source project. So for example, in this chart, you see it starts in 2016 and it goes through this last month in 2020. In 2016, there were about 500 stars on the GitHub project. On the GitHub FreeCAD project. FreeCAD moved to GitHub in 2011. So over 5 years, it accrued 500 stars, or about 100 stars a year. By early 2018, that had increased to 1,200 stars. Something happened in about a year and a half where the number of stars almost or went up by about 2.5 times, right? That's a substantial amount of growth in a much shorter amount of time. And what was going on? Well, I can tell you because I was there. We were starting to see some major improvements in FreeCAD stability. It had a bad history of crashing in really bad times. We're starting to see features that have been in it a long time but not very well developed really start to take hold and become really solid and stable and useful. And as a result, it started to get more attention. Then in 2018, that rate doubled, and that doubling of stars that rate had continued all the way until this year in 2020. And the reasons for that, again, was because we'd seen increases in development as more people have been attracted to the project, increases in stability and new features and things like that, better release cycles, right? So what you're seeing then in the first two trend lines is this nice consistent growth that says internally a lot of good things are going on with this project. And you're actually seeing what we like to call, you're seeing a project approaching what we like to call critical mass in open source. And critical mass is a point at which a project in open source becomes viable. It becomes sustainable. That if the lead developer or two developers kind of fade away or disappear, the community will step up and they will make sure this project continues to go because they love it that much. So what we're seeing here is an indication that FreeCAD is hitting critical mass, and that's a very, very good sign in the life of an open source project. Now, what I haven't talked about is at the very end, things went vertical on us here in just the last few months. Why is that? Well, if you're a hobbyist user of Fusion 360, which is one of Autodesk's tools, you probably know Autodesk changed very significantly the terms of use in their end user license for Fusion 360, specifically for free users. They took away a lot of features that the free users were enjoying very much. And if I understand it correctly, that if you were a free user of Fusion 360, you had to migrate your data out of Fusion 360 by, I don't remember, the end of September or something, or you were simply going to lose access to it unless you paid for a subscription. Some kind of dirty pool on Autodesk's part. Now, did it hurt them? No, they obviously didn't care about their free users. What they cared about was tightening up their bottom line. And chances are they had a lot of enterprise users who were using the free license because they didn't need all of the enterprise level features and they wanted to save money on a license. So chances are that's what happened. So did this hurt Autodesk? Absolutely not. Did it help FreeCAD? Oh my, yes. We have seen growth in the FreeCAD forums like we have never seen before. And I guarantee you that this jump is going to create a new momentum, and it's going to increase the level of development in FreeCAD projects to much greater levels than I think we're used to uh, in the coming months and years. So when I started getting involved in the FreeCAD project a couple of years ago, I came to it because I wanted to know if we could use FreeCAD for highway design. I'd already been exposed to Bentley Microstation and what they were doing. And I was really kind of frustrated with it because while it worked, and it certainly works better now than it did when I was using it, it crashed a lot. And it didn't work as intuitively as I felt it should. There was just, you felt like you were supposed to be able to do things in it that you just could not do. So it wasn't a sustainable system for doing 3D highway development in my mind. And I'm like, there has to be something better. And so I went looking, and sure enough, I found FreeCAD. Now, can FreeCAD do highway design better than Bentley Microstation? No, of course not. But it had some levels of, it had some things going for it. Like for example, it was a parametric modeler from the start, whereas Bentley Microstation is not. But it had a lot of things going for it that really made it more appealing to me. And so what I'm going to do now is we're going to get into, give me just a second here, we're going to get into FreeCAD, and I'm going to talk about a little bit of what that takes. We're at 12:30, so I got 20 minutes. Okay. So right now I'm running FreeCAD 0.19, which is the current development release. We're hoping to make this the stable release here soon, as in maybe a month or so. I'm not really sure. This is the FreeCAD user interface. It's not that different actually from the professional environments. It's very simply laid out. You have on the left-hand side, you have a model and a task. You have a couple of tabs with a model view that shows the hierarchical model as you develop a piece of a model. And down below are properties of objects that you select. There's also a task panel for specific tasks that you perform on an object. Down below, you have the report view where errors are often shown. And on the right-hand side here, we have the Python scripting console, which allows me to interact with the FreeCAD under the hood real-time using Python. So for example, if I want to, oops, if I want to print the sum of 2 and 4, I can type print 2 plus 4, and sure enough, Python tells me it's 6. So this is like a live Visual Basic coding console that I can use to interact with FreeCAD if I want to. So when you open FreeCAD, you get a start screen, and there's a number of example projects, a couple finite element analysis projects for structures, a part design example for creating complex parts, Let's see here. There's an architecture example. One of the developers is a professional architect, so he's worked very hard on developing FreeCAD for BIM and architecture. And then there's a robotic arm example, so that would have things like assembly, which is a key component of parametric CAD as well. And then at the top are recently loaded models. And so I'll load that Apple joystick model real quick just to show you a non-civil engineering use for it that I've used it. There we go. So here's that Apple IIe joystick model. And as you can see, I can hide elements. And I've designed this as several bodies so that it can be modified individually. And as I go through the model here on the left-hand side, you can see that I can show the pieces as they were originally created. So for example, there's the box that I used, and then I can select the thickness modifier, and that shows how I made it into a shell. And I can step through the model, and I can see the exact history that was used to build this model. Again, that is something that is not available when you use more traditional 3D methods, and it's really invaluable, especially when you're dealing with engineering design. But of course, my interest was not this to begin with. Now that I'm very much into 3D printing, I love designing stuff in FreeCAD. But my initial interest was highway design. And can I use FreeCAD to do highway design? And so as I explored the features of FreeCAD, one of the things that I came across was the Sketcher, which is a 2D geometric modeling tool that allows you to create complex cross sections for extrusion. So you can create more complex 3D shapes than using the traditional approach of combining, say, a cylinder and a box together and doing a subtraction to put a hole through the middle of a box. Excuse me. So just to kind of give you an example, I discovered the Sketcher and I started playing around with it. And it was the neatest thing to me. I'd never seen anything like it. So for example, if I want to create maybe just a simple box in the Sketcher, I can use the box tool to do that. And you see that when I create the box, it constrains each edge using a horizontal or vertical constraint. And what that means is no matter what I do to the box, the sides always remain perfectly straight. If I happen to delete, for example, the horizontal constraint on the top, I can now create a trapezoid shape. So the Sketcher allows you to generate this geometry and apply various constraints to a piece of geometry or across several pieces of geometry to define relationships and make sure that they always maintain those relationships. And that's a really neat feature. And the more I got into that, the more I realized this would be a perfect tool for highway design. If I wanted to lay out a highway, for example, I just needed to create a tangent, maybe do a simple arc, draw another tangent like that. No, don't want that there. And then maybe we'll add another arc like this. Let's make that a 2-center curve. And throw another tangent on at the end for good measure. So there we go. I've just created a highway alignment in FreeCAD using the Sketcher. Whoop-de-doo. And it's not even that great because as I adjust it, clearly we have issues. Because geometry in highway design is very tightly constrained. All of the elements in a geometric design are constrained to one another tangentially. And so in order to make that happen here in Sketcher, I simply need to select 2 elements and apply a tangent constraint. So if I go through and I do that with my 2 elements, I haven't figured out how to get rid of that annoying dialogue. It's annoying. Here we go. If I apply those tangent constraints to those elements, now I've got a highway alignment that means something. If I sit there and make adjustments to the alignment, there's a center point of a curve, the relationships between the elements are retained. Now, it may not move the way I want it to, but at least it remains a coherent alignment. Well, sometimes. One of the problems that I encountered in the Sketcher is a generic 2D geometric solver that solves geometry systems of equations for geometry based on the relationships, the constraint relationships that are defined. So if I mess around with it and do something wrong, and we'll see if we can get it to do something wrong here. Yeah, see, it's doing it. I just can't get it to stay. Almost. There we go. So this, to the Sketcher, is a perfectly valid geometric solution. And of course it is. The constraints are retained. This is an arc. Straight sections are there. it's perfectly valid as far as the sketcher is concerned. But in highway design, this is utterly useless. We'd never design a roadway like this. We don't even want to see a constraint like this, because in highway design, there's a lot of other constraints that the sketcher can't apply that are also taking effect. And while I tried to add them in after the fact, in the end, I just could not make it work in the sketcher the way I wanted it to work. So I realized while the sketcher was a fantastic solution, at least it gave me a starting point, but it wasn't really what I needed to use. So I abandoned the sketcher, not entirely, but largely abandoned the sketcher, and I started coming up with my own solution. And because FreeCAD has its, which by the way, this is the sketch, the sketch itself is stored as an object in FreeCAD, so it exists as an entire object if I click on the object that lets me edit it. But as I started working on this, I started thinking about this, I realized I needed to be able to manipulate FreeCAD at the lowest levels. I didn't want to use FreeCAD's pre-built objects because none of its objects were really suited for what I wanted to do. I had to have some way to create my own objects, stuff that didn't show up in the FreeCAD application, but let me at least draw on the screen. So I needed to be able to interact with FreeCAD's drawing level, which is called a scene graph. It's a very low-level drawing mechanism or drawing layer, okay? I needed to interact with FreeCAD's scene graph so I could do real-time visualization to help me prototype and develop engineering tools in FreeCAD that didn't otherwise exist. And so I ended up building a Python library called Pivy Trackers. There's probably about 8,000 lines of code now. I actually haven't looked at it lately. But I built a Python library called Pivy Trackers, which again, and the name is utterly meaningless unless you get into the nuts and bolts of FreeCAD. And I use that to generate this real-time visualization framework that I could use to prototype engineering tools more quickly in FreeCAD. And the result of that was the beginnings of a highway design alignment tool. And I haven't spent so much time on highway design alignment as I have developing that visualization tool because it's so important in doing what I need to do in order to be able to grow an open source engineering solution in FreeCAD. So in order to do that, what I've done is I've actually created my own workbench called FreeCAD Trails. And FreeCAD Trails is intended to do highway design and railway design because they're both based on the same math. And one of the first things I did in FreeCAD Tools was I added an importer that allows me to import land XML files. And land XML, of course, is a generic XML language that allows you to transfer, highway design alignments and vertical curves and horizontal curves and that sort of thing between applications that otherwise might be proprietary and might not share data very well. So using that, I created an alignment for Sugar Grove Road, which is just a few miles north of where I live. And if I open it, the importer looks inside the file and it identifies that I have 3 alignments in my land XML file: Sugar Grove Road, Penrose Road West, and Penrose Road East. And as I pick one, it tells me what curves I have in it, what station equations are there, how long it is, the starting station, and some basic other metadata. So once I've picked my alignment, I simply click OK. Give it a second, and there we go. And FreeCAD then imports my 3 alignments. And if I go over here and I look, I can see under my alignments group that I do in fact have 3 distinct alignments. And these alignments actually exist as sketches. So I am using FreeCAD Sketcher to generate those initial alignments, but I am not using the sketcher to edit them. To edit them, I pick the alignment that I want to manipulate, and I choose my editing tool. And once it comes up, it takes just a bit because there we go. Takes a bit because it's doing a lot of debugging in the background. Once it comes up, you see that it generates its own geometry on top of that original alignment. So it's taking the objects or the geometry from the sketcher and it's producing its own geometry. And that geometry is correlated to how a highway design engineer thinks. So for example, we have the major tangents of the alignment. And then in between the tangents, we have the curves at each internal PI. And each curve has its radius lines and its center point. And using this, I have a much more capable way of editing highway alignments. So for example, if I want to change the shape of this curve, I simply need to click and drag. And you see that it creates this blue dotted outline, which shows how I've changed the curve based on my dragging. If I drag it too far, you see it turns red. It turns red because I am now overlapping the curve just below it. So that is an invalid solution. And I'm getting a visual feedback on that because in the background, I've written into the Trails library an arc generator that's recalculating the math every single time I move the mouse. So I can sit here and I can adjust my curve, let go. Whoops. There's a few bugs. There's a few bugs, and kind of because we're running in Zoom here, it's a little slower, and I think that's kind of causing problems with FreeCAD. So we'll get that restarted. But what I've done is I've rebuilt Trails. I've built Trails to do all of that math in the background and to recalculate and to give me that visual feedback that I need so badly in order to do real-time 3D engineering. We'll give this another shot because there's a little bit more I want to show with how Trails works before I move on. And yes, Python is a little bit more susceptible to bugs, especially when you're in a sluggish environment. If I coded this in C++, which is the higher performing language, it would certainly work a lot better. But for the purposes of prototyping, Python is entirely adequate in most cases. And yes, we have a long wait again. If you notice here on the left-hand side while we're waiting, if you notice here on the left-hand side, I designed a dialog, a task view that gives me real feedback on the elements as I select them. Right now, I don't think I have any of that hooked up. No, I don't. I don't have any of that hooked up. But anyway, I can sit here and I can adjust my arcs and my curves. And you can see as I adjust my tangent, as the two arcs overlap, they go red because, again, it's doing that real-time validation. I can even pick a tangent, and if I hold down the Alt key, I can rotate them like so. And I'm really free to do whatever I want with this highway alignment, even if it's not at all valid. And there we go. Yeah, another bug, but that's okay. Like I say, that's just lag messing with the Python. Anyway, so that gives you an idea of what the value then is of taking the time to actually build this low-level language and what it takes to generate or what it takes to start to grow, if you will, an engineering tool in an open source domain where it did not exist before. Note that I'm standing on the shoulders of giants. I'm using an existing application, but I'm repurposing it for purposes for which it was not originally intended, but are entirely acceptable purposes insofar as it's meant to do. There's a couple other things I want to show. And I restart FreeCAD every time just because, again, things written in Python are a little more susceptible to bugs, and all of this is in development as we speak. So one of the other tools that I developed in using Pivy trackers, using this visualization library, is a swept path analyzer. Last year, when I started working in the FreeCAD forums, I met one of the more genius, I guess, forum contributors. He goes by MicroLE on the forums. He's a German teacher, and he and I started talking because he was interested in my professional experience, and he says, I've always wanted to do railroad design and be able to bring in 3D terrains and lay out railroads and do that sort of thing in FreeCAD. I think that'd be so neat. And I says, that sounds like a great thing, because railroads and highways aren't that far apart. And so we started working together, and he kind of taught me the internals of FreeCAD and got me really going on it. And then a little while later, a professional engineer out of Georgia, he's actually the city engineer for Athens right now, showed up, and he said, what would be really cool is if we could do a swept path analyzer in FreeCAD, an open source swept path analysis. And he says, there's some free tools out there, but none are open source. And the only other option is AutoTurn. And, a lot of people could really benefit from having swept path analysis for whom having to pay for an AutoTurn license would just not be a great idea. And so I said, yeah, that's a great idea. So MicroLE, Thomas, his name is, he says, oh, what is this? And so we explained it to him, and he started doing some research. Oh, Ackerman steering. So he laid down the code for doing Ackerman steering, and he got a demo working in FreeCAD. Now, it wasn't a particularly useful demo. He didn't design it with with an engineering use in mind. He was just trying to prototype something and make something work. So when he was done with it, I took the code that he had written for Ackerman steering, and I reworked it, and I tried to build or prototype a swept path analysis tool. And so I created another workbench in FreeCAD called FreeCAD Turns that does that. And FreeCAD Turns, right now I've got a couple of tools set up. The first one is a path creation tool. And to do that, I simply use the sketcher, because while it may not be great for highway alignment design, it is entirely adequate for generating a swept path analysis path. So here I'm using the sketcher to create a spline, hit close, and it did not generate a spline. Let's try that again. I'm starting to think Zoom and FreeCAD are just not good buddies. There we go. Okay, so maybe I picked the polyline before. So anyway, I use a sketcher to create a swept path, a spline. And then I have another icon, which I haven't bothered to give him pretty pictures yet, because frankly, I don't care. Oh no, yeah, we'll pass on that. So anyway, it does work, but again, FreeCAD and Zoom just must not be great friends. Here's a working demo. Go away. Here's a working demo then of Turns doing a swept path analysis that I published as a GIF some time ago. As you can see, this is just a single unit vehicle, but it does track down the spline path, projects what the radius of turn is, and it also tracks the individual trails that the vehicle follows. It's animated, and you can increase and decrease the speed. I have all of the individual templates put in for the from the AASHTO Green Book. They're not all. I don't have multi-unit vehicles figured out just yet. Well, I do have them figured out. I just don't have it fully implemented just yet, because I did this for a couple of months a year ago, and I haven't touched it since. But you can see how I was able to use Pivy trackers then to prototype a perfectly functional, reasonable demo of a swept path analyzer using open source tools. And it really, to me, the real value then of growing open source tools is having access to libraries like this that allows you to quickly modify an existing framework to do the things that you need to do for whatever the specific tool may be. So one other thing I want to show in FreeCAD, so we'll try this one more time, and hopefully it won't crash on me here. Like I said, I've never done it in a Zoom demo, and I've never seen this happen before. So it has to be because of the screencasting. Oh yeah, by the way, glider workbench. Let's see. Somebody create a glider workbench. You turn on the glider workbench, you pick a glider, and that gives you a default glider to start modeling and creating gliders with. I mean, I don't know anything about gliders, but I think that's awesome. Anyway, we'll discard that. And one of the other things that's really neat, and this is neat just because this I've never had this happen to me before, is I started this thing, right? I started this thing in open source, and people started showing up. Not a lot, but a few interested people, and that's really all that mattered. And so this guy from Turkey shows up who's a surveys engineer, geomatics as he calls it, which I had no idea geomatics meant surveying, but it does. And he wanted to create a terrain modeler. He wanted to be able to import 3D data as a terrain, build a surface for it, and things like that. And again, we'll see if FreeCAD will behave for us on this one, because and so he did. And he called it the geomatics workbench. And then as we were going back and forth, he started using a lot of code from my stuff, because I had a lot of things figured out, like calculating orthogonals to a center line, or doing stationing, or things like that. And he wanted to be able to cut cross sections, so he was going to need stuff like that. So he started using a lot of the code that I'd written in my Trails workbench in his geomatics. And over time, it just kind of made sense that we merge them together. So the other part of Trails, if you ask me, the more interesting part, is the geomatics side. So he sent me some files that I could use to demo this to you guys. And where is it? I think it begins this one. And so he sent me 3 files. They're all of the same area, so they're all interconnected. And these are just geopoint files, right? And they contain northings, eastings, and elevations, and then an individual point number for each point. Nothing too crazy about that. And he has an importer built that lets you load it in. And all you do is click import, and you see that it comes in quite nicely. So there's your 3D data. And actually, there are several importers built into FreeCAD. Excuse me. OSM, CSV, GPX, there's LiDAR and that sort of thing. I don't know that all of them work, but many of them I know do. But one of the neat things that you can do once you import it, it creates a set of points. And one of the neat things that he's got working is surfaces. So I can choose my points and hit create, and it generates a surface. Oh man, his stuff works way better than mine does. And here we have a 3D surface of those points. And one of the neat things he's added recently that just thrills me is that he's added contour lines. And it looks gorgeous to me. I don't know. I'm just thrilled, kind of because somebody showed up and started doing their thing on my project and it looks great. And it's, yeah, and in the end, it's not really my project. I mean, I just had an idea and this is really all his thing. And I don't know, I'm thrilled. It's really neat when someone else shows up and says, hey, this is really cool. I want to do something too. And so bit by bit, we're starting to see that come into FreeCAD Trails, and he's doing more development on it consistently, and other people are starting to show up and are taking interest in it and trying it out. And hey, this doesn't work, and giving us bug reports, which really helps us make the tools more useful. Again, is this useful in professional context? Of course not. Not in a real production environment, and that's understood. But this is how it becomes useful, bit by bit. And the more interest we get, the more momentum we gain, and the more momentum we gain, the closer and closer it becomes to actually being useful at various levels in production environments. So that is really all I had to present today on FreeCAD. So I'm going to conclude with that, and we'll open it up to questions.
Just as a reminder, I know we're on a different platform today, but there is a question and answer section. If anybody has any questions, go ahead and pop those in there. Joel, do you have any contact information that you could provide in case we get any questions after the webinar is over?
Yes, and I'll just, here, let me just kind of open something so I can, okay, right, that'll do it. So my email, and I'll just type this out here. My name, Joel Graff, my email, I don't think I can I increase the point size in this? I've never used it. Is joel@thinkopenllc.co. And so you can reach me there.
Awesome. Well, I'm going to go ahead and say if anybody has any questions, go ahead and send them to Joel or myself. Joel, I want to thank you today for such a great presentation, and to everyone who joined us. Another special thanks to everybody who's joined us throughout our virtual presentations of 2020. This was our final first Friday of the year. We're hoping to have information regarding our 2021 education lineup coming shortly, so stay tuned. I hope everybody has a wonderful rest of their weekend as well as the holiday season. Please be sure to complete your quiz by Monday so we can send certificates out in a timely fashion. Again, thanks everyone, and Joel, have a wonderful rest of your day.
Thank you.